In this video, we're going to cover AP Physics 1 Unit 2. We're going to cover the first half, which is going to be on forces and Newton's laws. A force is a push or a pull, and the unit for force is newtons. We're going to take a look at some common types of forces. The first one is gravitational force. Another name for gravitational force is weight, and this is defined as the force of gravity. If you know the mass of an object, you can calculate the gravitational force by taking mass times g. Mass is the amount of matter in an object. If you take an object to the moon, the mass of the object will stay the same, but the gravitational force, the weight of the object, will be different because g, the gravitational field strength on the moon, is different than on Earth. On Earth, it's approximately 10 newtons per kilogram. On the moon, it's approximately 1.6 newtons per kilogram. The normal force is a support force. So if you're standing on the ground is pushing you up. That is the normal force. It is defined as the force that a surface exerts on an object, and this force is perpendicular to the surface. An example of this is when you stand on a bathroom scale. The bathroom scale is pushing you up, and you can look at the number on the bathroom scale to find out what the normal force is. And that's also your apparent weight. So imagine if you were to put the bathroom scale in an elevator and it's accelerating upward, your apparent weight would be greater than your weight would be because you are accelerating upward. If there is no normal force acting on you, then you would be in what we call weightlessness. You would feel weightlessness and you would be in free fall. So weightlessness doesn't mean you don't have a weight. It just means that there's no support force, no normal force pushing you up. Tension force is defined as the pulling force due to a string, a rope, a chain, cable, etc. And so the direction of the tension force is along the direction of the string. When you see the term ideal string, that refers to a massless string that doesn't stretch. Here's an example of some forces, and this is called what we call a force diagram. Notice that the forces start from the center of mass of the object, and they point in the direction that the force is acting. So here we have a string that's connected to this block, which is on this incline. The force of the string, we call this the tension force. The force of the surface pushing on the block, we call this the normal force. Notice that it's perpendicular to the surface. And gravitational force is always going to be downward towards the center of the Earth. And if we know the mass, which is 5 kilograms, we can calculate the gravitational force by taking Fg equal to m times g. Next, we'll take a look at friction forces. So there are two types of friction forces. The first is kinetic friction. This is the force that acts between two surfaces that are sliding past each other, and the direction of the kinetic friction force is in the opposite direction of the motion. The equation for the kinetic friction is mu k times Fn. Fn is the normal force. Mu k is the coefficient of kinetic friction. This tells you how much stickiness there is between the two surfaces. When you use this equation, you'll notice some absolute values because mainly we're looking for the magnitude of the frictional force. And then as far as the direction, you just remember that the direction is in the opposite direction of motion. Static friction is when an object is not moving relative to the surface. So we define it as the force that prevents relative motion between two surfaces. Now, it doesn't mean that it's not moving. For example, you could have a pickup truck and a box in the back of the pickup truck, and the pickup truck is moving, but the box is not sliding relative to the pickup truck. So we want to be careful when we say that the object is not moving. We're talking about the surfaces are not moving relative to each other. The equation is very similar to kinetic friction, but there is a little bit of a difference. So for static friction, it's less than or equal to the coefficient of static friction times the normal force. And notice that it's less than or equal to, because if there's no external force causing it to move, then there's no static friction. If you push it a little bit, there is static friction that has the same amount of magnitude but in the opposite direction. As once you exceed this mu times Fn, this amount right here, then it starts to move. So it's not automatically equal to mu s times Fn. This is what we call the maximum static friction. But if you only push the object with a little bit of force, then you're going to have a little bit of static friction in the opposite direction, balancing the forces. But once you go above mu s times Fn, then the object will start to move. On the left, we have a box on an incline, and this box is not moving. The velocity is equal to 0. So what are the forces acting on this box? So I like to always start with Fg because all the objects will have gravitational force pulling on it. So that's going straight down. The normal force is perpendicular to the incline, so it's in that direction. And then the static friction is going to be along the surface, and it's preventing it from sliding down. So the way I like to think about static friction here is imagine there was no static friction. Which way would the box go? And the box would slide down. So the static friction, to balance that, has to be in the opposite direction. So I know it's going to be towards the top of the ramp. On the right here, this is a box connected to another box through a string, and there's a pulley here. This is called a modified Atwood's machine. And we'll start with the box on the table. So there's gravitational force down, normal force up, there's tension to the right, and if there is friction, the kinetic friction will be to the left. On the right, the mass that's hanging on the string, we have gravitational force down and tension force up. Now, a common mistake that students make is that they think that the tension force here and the gravitational force here are equal, but if this object is accelerating downward, then there has to be a net force. So Ft has to be less than Fg. So don't fall for that trap there. Know that if this object is accelerating, then the forces have to be unbalanced. Let's say that this surface between the surface and the block and the box has a coefficient of kinetic friction of 0.2. What is the kinetic friction? Well, if we know the gravitational force is 10 newtons, let's say we're given that, then we know that the normal force also has to be 10 newtons because it's not accelerating up or down. And then we know that Fk equals mu times Fn. Mu is 0.2, Fn is 10, and we get Fk is 2 newtons. Now we'll take a look at Hooke's law. So Hooke's law relates to situations where you have a spring. So it is the force needed to extend or compress a spring by some distance. What it's saying is that force is proportional to that distance. So if you have a spring here and you pull it to the right, there will be a spring force pulling it to the left. If you compress it to the left, the spring force will push it to the right. The equation for the spring force is equal to negative kx. That negative just says that the spring force is in the opposite direction of the displacement. On your equation sheet, it has absolute values. So typically when we use this equation, we're just trying to get the magnitude, and then the direction we can figure that out because it's going to be in the opposite direction. The spring force will be in the opposite direction of the displacement. K is what we call the spring constant, how stiff that spring is. If you graph the spring force versus the displacement, then the slope will represent the spring constant. A more stiff spring will have a bigger slope. A looser spring, less stiff spring will have a less steep slope. Now we're going to take a look at Newton's first law, which states that an object at rest will stay at rest and an object in motion will stay at constant velocity unless acted upon by an unbalanced force. Another way to think about unbalanced force is the idea of a net force. So if something has a net force, that means it has an unbalanced force. Equilibrium, when you see that term equilibrium, it means that the net force is 0. Whenever the net force is 0, you know that the object is at rest or moving at constant velocity. And you can go the reverse of this. You can reason that if an object is at rest or moving at constant velocity, then it must be in equilibrium. The net force has to be 0. So it goes both ways. Let's take a look at this pie pan here. It's got 1/4 of it cut out, and we've got a ball that we're rolling around. And once it gets to this point, which way is that ball going to go? Is it going to go along path A, continue in a circle, path B, straight ahead, or path C, is it going to roll away from the plate? The answer is B. And the reason it's B is because at this point right here, before it leaves the plate, it's going in that direction. So once the wall's not there, it's going to keep going. It's not going to go A because the wall's not pushing it towards the center here. And it's not going to go C because there's no force pushing it that way. So this is a pie pan, and we're looking from a top-down direction. So once it gets to the edge of the pie pan here, it's going to go straight path B. Another example of Newton's first law is this person on the skateboard. So this person is going to the right. There's a block on the ground, and when the skateboard stops, suddenly stops, the skater continues moving forward, and this is an example of Newton's first law because this person was an object in motion. And so even though the skateboard stopped, the person is going to continue to move in a forward direction until there is an unbalanced force. Next, we're going to take a look at an inertial reference frame. So an inertial reference frame is one from which an observer would verify Newton's first law of motion. Now, I find it more helpful to think about non-inertial reference frames. By understanding non-inertial reference frames, I think it'll help you to understand what an inertial reference frame is. Okay, so here we have a car that's going, making a turn. And so from the outside observer who is in an inertial reference frame, Newton's first law would hold. But the person inside the car has a non-inertial reference frame. As this person is turning, the person's going to feel like they're getting pushed outward. Even though there's no force from an outside observer, there's no force pushing the person outward. The person feels like they're pushed outward because they were going in this direction, and so their body tends to want to continue moving in a straight line. But the car turns, and that's a non-inertial frame. Now, this person in this car inside the car also has a non-inertial frame as well. When the car suddenly speeds up from the outside observer, we note that an object at rest tends to stay at rest, and so this person's head is going to kind of bob backwards because the person's head was at rest, but the person inside feels like they're getting pushed back, even though there's no force pushing them back. It's just the car is accelerating towards the right. Now we're going to take a look at Newton's second law, which states that acceleration is equal to the net force divided by the system mass. I like to write it this way: net force equals ma when I am solving a problem, but a equals net force over mass is, I think, more intuitive. So if you have a greater net force, you're going to have a greater acceleration. If you have a greater mass, you're going to have a smaller acceleration. We want to remember that anytime you have forces that are unbalanced, you will have an acceleration. The equivalence principle tells us that within a non-inertial reference frame, an observer cannot tell the difference between the sensation of weight and the effects of acceleration. So here's an example. We have this person who is in this room, and it's completely enclosed. There's no windows, and this person is on a bathroom scale. And so this person has a feeling of a sensation of weight. Now imagine another person in the same size room, no windows, they cannot see out. They're also on a bathroom scale, but instead they are in a rocket. They are in outer space, and this rocket is accelerating at 9.8 meters per second squared. Same thing as the gravitational field on Earth. These two people would not be able to tell the difference. They wouldn't know if they're on Earth or in the rocket ship. They would feel the same way. The bathroom scale reading would read the same thing. And so this is the idea of the equivalence principle, that within a non-inertial reference frame, these two people would not be able to tell the difference between whether or not they are on Earth or in a rocket that is accelerating at an acceleration of 9.8 meters per second squared. Now we'll take a look at the center of mass. The center of mass is defined as the average position of all the parts of a system weighted by their masses. The equation is the position of the center of mass is equal to m1x1 plus m2x2 plus ... divided by the total mass. A system's center of mass obeys Newton's second law. What this is saying is that if there is a net force on the system, then the system's center of mass will accelerate. If there is no net force on the system, or the forces are balanced, then the center of mass will not accelerate. The center of mass velocity only changes if there's a net force on the system. Here's the equation for the center of mass, velocity of the center of mass, and you'll see that it looks very similar to the equation above. This one is not in the equation sheet, but I just wanted to show you and let you see how similar it is to the other equation. So here's a couple examples of the center of mass. So on the left here, top left here, we have an object that is about to explode, break up into pieces. And so this is before it explodes. And then after it explodes, notice that the pieces are flying in all different directions. But the center of mass is still at the same location as long as there's no net force acting on the system. Now, let's say we took a tennis racket and we were to toss it and we were to rotate it as it, flip it as it falls through the air. Notice, even though that it rotates, the center of mass, which I'm representing with this green dot right here, notice how it follows a projectile motion, just as if you were to take a baseball and then toss it through the air, it would follow this path. So what this is telling us is that even though the tennis racket is shaped differently, not symmetrical. One side might have more weight than another side, and shape differently. However, the center of mass will still follow Newton's second law because there is a force of gravity downward. Vertically, it will accelerate, but horizontally, it's moving at constant speed. Now we're going to take a look at Newton's third law, which states that for every action force, there's an equal and opposite reaction force. Now we want to remember that action-reaction forces always act on different objects, and we refer to these pair of forces as the third law force pairs. Now I want to show you an example of an apple and the earth here, because a lot of times this will puzzle students, which is, how is it that the earth can pull on the apple the same force that the apple pulls up on the earth? So I want to take a moment to explain this. Now, I'm going to be using the agent-victim notation to notate the forces. So this FEA means that this is the force of the earth acting on the apple, and this right here is the force of the apple pulling up on the earth. Okay, and so you can see that these forces are equal in opposite direction. Let's first focus on the apple. So on the right here, we have the apple. The force acting on the apple is FEA, and the mass of the apple is very small compared to the earth. And so I'm going to, if we take a number divided by a very small number, we get a big number. So this A is very big. Now, the force acting on the earth, which is the FAE, the force of the apple pulling on the earth, this is the same force as the force of the earth pulling on the apple. However, the earth is way bigger. So I wrote down this really big M. And if you take a number divided by a really, really, really big number, you get a really, really small number. So the acceleration on the earth is very, very tiny. So yes, the force acting on each other is the same. The earth pulling on the apple and the apple pulling on the earth, equal and opposite forces. That's true. However, the acceleration is different because they have different masses. The apple has a small mass, a big acceleration. The earth has a huge mass, a super tiny acceleration. Now I'm going to go through the steps for solving force problems. Step 1, draw the system boundary. We want to make sure we identify what the system is. Even if you don't draw on paper, just mentally you know what it is. Number 2, draw the force diagram labeled. These are labeled arrows that begin at the object. Number 3, indicate positive direction. I suggest make positive in the direction of the acceleration, but you can make it in whatever direction you want, but oftentimes that is helpful to do it that way. Number 4, write the equation using Newton's second law for each direction. So I'm talking about F equals ma. And number 5, solve for the unknown. Okay, we're going to start with forces at an angle. Here we have a box. We're pulling at an angle theta. We're pulling with the force of F. And we're going to start with our force diagram. So it's on a surface, so we have a normal force perpendicular to the surface. It's going to be up. It's got gravitational force, it's on Earth, and so Fg equals mg, and then it's moving to the right, so friction will be to the left, and kinetic friction is equal to mu times n. We don't break up forces into components where we're drawing the force diagram. If they ask you to draw the force diagram on the free response question, do not break them up into components. Break them up into components somewhere else on the paper, which is what I'm doing on the right-hand side right here. So first, I'm going to make sure all the forces are on the x and y axis. I'm making right positive and up positive, so don't forget to indicate that. And we're going to use a little bit of trig. So the horizontal component is going to be f cosine theta because it's adjacent to the theta, and then the vertical component is going to be f sine theta because it's a opposite of theta. I'm going to write down Newton's second law for both the x and the y direction. I'll start with the y direction. Net force in the y direction equals MAY. And so I'm going to first write down all the forces in the positive direction, which is N plus F sine theta, minus the forces in the negative direction, minus mg. Since it's not accelerating up or down, it's going to be 0. If I solve for N, I get N equals to mg minus F sine theta. Now, horizontally, we're going to use F cosine theta here because that's the component horizontally. And what we're trying to solve here is the acceleration. We're trying to figure out what the acceleration is. So we have net force in the x direction equal to F equal to max. And so we have F sine theta minus mu n, this is the friction force, equal max. Now we're going to substitute mg minus F sine theta into for the normal force, and then we solve for a, and we divide m on both sides, and we get F sine theta minus mu times mg minus F sine theta parentheses divided by the mass of the object. Now we're going to take a look at a block that is sliding down an incline with friction, and we're going to first identify our system, which is going to just be the block. Next, we're going to draw our force diagram. Gravitational force is going to be straight down, equal to mg. Normal force is going to be perpendicular to the surface of the ramp, and then Fk is going to be in the opposite direction that the block is moving. The block is sliding down, so Fk is going to be up the ramp, which is equal to mu times Fn. Next, I'm going to indicate my positive direction. I'm going to make down positive and also make perpendicular to the surface going up, top up left, also to be positive as well. I'm not going to break my forces into components here. I'm going to do that elsewhere, which is over here. We're going to make sure we do that separately on the free response question on the AP exam. So now we're going to break our Fg into the perpendicular and parallel component. So the perpendicular component, perpendicular to the ramp, is going to be mg cosine theta because it's adjacent to theta. And then the parallel component is going to be mg sine theta because it's opposite of theta. I'm going to apply Newton's second law to the x and y direction. I'll start with the y direction. So net force in the y direction equals MAY. In the positive direction, we have N minus mg cosine theta. In the negative direction, equal to 0 since it's not accelerating in the y direction. So N is equal to mg cosine theta. On the x direction, we have net force x equals max. In the positive x direction, we have mg sine theta, which is right here, minus friction mu times n equals to max. We're looking for the acceleration, and so we're going to substitute the normal force mg cosine theta for the normal force. Notice that the m's cancel out, and we get that the acceleration in the x direction is g sine theta minus mu g cosine theta. You can also factor out the g as well. Now we're going to take a look at a two-body problem. This is a modified Atwood's machine. You have a block here connected to a rope around a pulley, goes down here, and then connects to another block. So when you take a look at two-body problem, we can set our system on one or the other one or both objects as our system. So I'm going to do all three of these so you can see how that works. So first, I'm going to make block 2 my system. I'm going to make down positive, and the forces acting on block 2 are Fg going straight down. We'll call this M2G, and then going up is the tension force. We'll call that T. And notice that these two forces are unbalanced because in this situation, this scenario, this block is accelerating downward. So be really careful. Do not set these equal to each other. It is accelerating, so they cannot be equal. These forces cannot be equal. Okay. So now I'm going to apply Newton's second law. F equals ma. Force in the positive direction minus force in the negative direction. M2g minus t equals M2a. Solving for t, we get M2g minus M2a. So if you're looking for the tension force, this is how you can solve it if you know the acceleration. Next, we have block 1, which is pulled to the right. We're going to make that our system, make right positive. The forces acting on block 1 are Fg, and we're going to call that M1g. Going up is going to be the normal force. Pushing up is the normal force. Pushing to the right is the tension force. And to the left is the kinetic friction force, which is mu times the normal force. Notice that the tension force here and the tension force here are going to be equal. It's the same string, and the force throughout that string is going to be the same. Now we're going to apply Newton's second law, net force equals ma, and we have the force in the positive direction minus the force in the negative direction. Tension force minus mu n equals m1a. Solving for t, we get m1a plus mu m1g. Now, if we want to solve for the acceleration, we don't know the tension, here's what you can do. You can make both of these blocks as your system, and we're going to apply net force equals ma. So what forces are acting on your system? What net forces? So there is a normal force and there's m1g, but these two are going to cancel out. So the two forces are m2g and mu n. You can think of this as normally we have our axis is straight. You can think of the pulley as bending our axis. So the object is going to the right and then it's going down. So it's kind of bending our axis here. So in the positive direction is m2g minus, in our negative direction is mu n equals, and be really, really careful here. This m is the system mass. Okay, it's the system mass. So it's m1 plus m2. Notice I drew my system boundary here. That's why that's so important. And then we're going to substitute the normal force we're going to substitute the normal force with m1g because we know these two are equal to each other. It's not accelerating up and down. And then we're going to divide m1 plus m2 on both sides. And we get that the acceleration is m2g minus mu m1g divided by m1 plus m2. So even though if you don't know the tension, you can still solve for the acceleration. Now we're going to take a look at a force problem, but that also involves Newton's third law. So here we have a hand pushing on block A, which is next to block B. And so block A is also pushing on block B. Now, when you see a problem like this, here's a key tip, really important, which is to understand that the acceleration of this whole system is equal to the acceleration of each of the items, each of the masses in the system. So the acceleration of A is equal to acceleration of B, which is equal to acceleration of the whole system. So if you know this is usually not stated in the problem, but if you know that they're accelerating together, that's going to really, really help you out. Okay, so I'm going to break this up into 3 systems, and then we're just going to analyze them. So we'll start with the first one. So we're going to make both of them our system. So net force equals ma. This is the hand pushing on the 2 blocks. The system is ma plus mb times the acceleration. Note that the system mass is ma plus mb. Really be careful of that. All right, now if just A is our system, now we're just looking at just A. We have the hand pushing this block to the right, and then I'm using my H and victim notation here. This is the force of B on A, and notice there's a force pair here. This is the force of block A on B. So these 2 forces are equal in magnitude, but in different direction. Here's the Newton's second law equation for this one, F equals ma. So we have FH in the positive direction, I'm making right positive, minus FBA, which is to the left, equals to, and notice here, my system mass is ma times the acceleration. For block B, the net force equal to ma. The net force here is FAB. This is the force of A pushing on B equals to the mass of block B times the acceleration. And remember, the acceleration of all of these 3 systems are going to be equal to each other.